Hi, myself Mrs. T. Neha, working as Assistant Professor in Civil Engineering Department at Marri Laxman Reddy Institute of Technology and Management. So now today I am going to give a video lecture on Theory of Elasticity and Plasticity subject, which is a prerequisite of Strength of Materials, which we study in BTech, and this subject is about MTech Structural Engineering, and this is a main subject which we can understand everything, the materials, properties of the materials like elasticity, plasticity, and where we can use these materials. So we can use these materials, we can know these properties of all the materials which we use for construction, so like aggregate, concrete, everything, and next where the material we can construct everywhere. So to study about all the materials, we require to know about what is the plasticity and what is elasticity. So generally now we are going to discuss about this subject, basic topics from this. So the subject is Theory of Elasticity and Plasticity. This is a MTech Structural Engineering subject, and the prerequisite of the subject is Strength of Materials, which we study in BTech Civil Engineering. So now these are the course objectives of the subject, and the objectives of the course means what are the objectives which students will be able to learn from this are to define stresses, strains and equilibrium and compatibility. So these are stresses, strains, these are the most important factors and most important properties of the material which we need to understand to any construction, to build anything, any structure or else anything. So these are the main properties which we have to know. And next, to derive the governing equilibrium equations. Basically, the equilibrium equations are most important equations which we know, and they are the basic equations which we learn from BTech UG in civil engineering subjects. And next, to understand stress and strain relationships. So these stress-strain relationships gives us, so nothing stress and strain relationship, how the stress occurs, how the strain occurs, how the deformation occurs, the relationship between these two, and everything we'll learn in this. And next, to apply the concepts of elasticity and plasticity to solve engineering problems, structural engineering problems. So here, concepts of the subject is about elasticity and plasticity. Basically, these are the general materials, general things we know, that elasticity and plasticity. So now we are going to learn in depth in this subject. So next, again, when coming to the course outcomes, after the completion of this course, the students will be able to explain the concept of stress tensors, equilibrium equations and stress transformations in 2D and 3D. So after learning from unit 1, we'll have about stress. So in that stress tensors, what are the components of stress, what is elasticity, plasticity, etc. we'll learn there. So this is the CO1. And next, classify strain components and compatibility conditions in different coordinate systems. So for anything we require coordinate system, and like 2D and 3D, and next, where there are stress components, we will have definitely the strain components. So deriving those strain components and compatibility conditions. And next, analyze stress-strain relationships, material symmetries and related idealizations in elasticity problems. Next, compare stress-strain relationships and material symmetries. Evaluate relations in material symmetry. So these all things will every student will come to learn about this after completing this course. Next, when coming to the syllabus, this syllabus is structured in 5 units in Theory of Elasticity and Plasticity subject. So when coming to the syllabus, unit 1 will have about stress, complete stress, what is introduction, definition, everything, stress, types of stress, components of stress, etc. we learn in this unit. And coming to unit 2, it is about strain. So when there is a stress, there will be automatically strain. So we learn about strain. Next, unit 3 is stress-strain relationship. So in unit 1 and 2, we will learn stress and strain, about both. Now in this unit 3, we will come to learn about this both relationship. How is the behavior of a material under the stress and strain. And next, solution of 2D and 3D elasticity problems. Means like problems by using the above properties like elasticity, plasticity, stress, strain and some other elements. So we'll solve some of the problems. And next, last unit is unit 5, which is plasticity. So how much important is the elasticity, that much importance is the plasticity. So we'll learn all these things in this subject. So now let's go with unit 1 in the subject. Unit 1, which is about stress. So in stress, the first topic, basic topic is introduction. So first of all, basically introduction is about elasticity. We'll learn basic thing. Main, we know what is elasticity means. The elasticity is defined as whenever a force is applied on a body or any material, then again it comes to regains its original position within the elastic limit after removing the applied load. So this condition, when any material, if it regains its original position after the removal of load, then it is considered as elasticity. Again, when coming to the plasticity, it does not regain its original position under the removal of the applied load. So basically, if we take any example of this, next, this elastic deformation. The deformation when we deform a body means either we stretch it or we compress it or we twist it, some deforming forces will be occurred. So due to those deforming forces, the strain or the deformation of the body occurs, means the length will be increased, or else the length will be shortened, or it will be twisted. So anything may happen. Due to this, the original shape and size of the object or any material gets changed. So after removal of the applied load, again it will be regain its original position within the elastic limit, means to certain extent. For every object there will be certain elastic limit and certain plastic limit. Beyond the elastic limit, if the under the removal of the applied load, the body does not regain its original position, then we call them as the plastic materials or plastic bodies or else plastic behavior. So let us see, and this elastic deformation is temporary. And when coming to the plastic deformation, this is a permanent deformation which does not regain its original position and original size. And here are a few examples of elasticity and plasticity. First thing is, this is the we'll see in our daily life that a rubber band, when we stretch it to certain elastic limit, it will regain its original position. When we release it, when we stretch it and release it, it regains to its original position. And next, when we take this sponge, when we squeeze it, it decreases its volume, but again when we release it, it regains to its original position. So these both are the completely elastic properties. And when coming here, this is the rubber band, and to certain limit, if we stretch the rubber band, in the elastic limit, it will regains it to original position. And next, when this coming to here, this is the paper pin. So this paper pin we'll use for papers. So this pin, when we stretch it, again it cannot regain its original position because it does not have elastic behavior. So this material is plastic material. I mean plastic material is plastic, which shows the plasticity behavior. And next, when coming to these bottles, so these plastic bottles, when we apply load on it, to certain extent it can deform, but so beyond the limit, it cannot regain its original position, which shows the plastic behavior. And next, these cups or small paper cups or anything. So these is also complete the examples of plasticity. So now these elasticity and plasticity before we have seen are the basic examples and basic definitions. So how we are including these examples and these studies to the theory of elasticity and plasticity subject, and that we'll see now. So here, elasticity refers to the ability of a material to retain its original shape and size after the removal of an applied load. So when coming to the engineering vocabulary, how we can define elasticity and theory of elasticity is, when the stress is when a stress is applied on the body, means when stress is applied means like when we are applying any load on the body, it induces stress. And when it is inducing stress, automatically it can induce strain. So with this as per Hooke's law, he gave the statement that stress is directly proportional to the strain. When there is inducing of stress, there will be strain also. So this elastic behavior is nothing but which the material within the elastic limit, it regains its original position under the removal of load. And next, some example, bending of a steel bar. So as we know, there are steel bars in different number of sizes. So we'll take minute like an 8 mm or 10 mm. When we bend the bar slightly with applying some load, basic load, then automatically it can regain into its back position, which is having elastic behavior. So here in this theory of elasticity, we'll have again two key components like stress and strain. So here, stress is nothing but the internal force per unit area within the materials, and strain is the deformation resulting from the stress. So whenever the deforming forces occurs, the strain also occurs. So when there is stress, there is strain. So the relationship between stress and strain is they are both are directly proportional to each other. And next, the stress is proportional to strain within the elastic limit of the material. For any material, while applying the load, the stress will be induced, and directly the strain automatically the strain also gets induced. So from this we get that stress is directly proportional to strain as per Hooke's law. And next, when coming here, elasticity moduli. So for every material there will be some elastic limit and there will be some elastic property. For all the materials there will be some. So for every object. So how we can see how they are quantified by their material property. Here first one is Young's modulus. So it measures the stretching capacity, tensile elasticity. So when tensile is nothing but when we are stretching an object through a force stretching, so that it shows the modulus, Young's modulus will measure this tensile elasticity. And next, coming to shear modulus, it measures shear elasticity. Shear is nothing but the sliding property of any material during the application of load. Next, coming to the bulk modulus. So it measures the volumetric elasticity, means compression. So we have tensile, when we have compression, all these types of stresses. So we'll learn about them later on. So now just we are thinking about basic. Next one is elastic limit. So the maximum stress that can be applied to a material without causing permanent deformation. So the elastic limit is defined as whenever we apply a load on the body, so it deforms to some shape and size. So again, under the removal of that load, it regains its original position and size. So it is up to some certain limit which is known as elastic limit. And next, beyond that is the elastic limit, and the property objects which shows this property are known as elastic property, elastic behavior. And next, beyond this elastic limit, so if we take a rubber band, up to some extent if we stretch it, it regains to original position. But later on, if we pull with much force, then it cannot regain its original position. It can regain to back, but it cannot come to original position. That beyond stretching something or compressing something beyond the elastic limit is known as the plastic behavior. So next, theory of plasticity. Next, plasticity is behavior of materials that undergo permanent deformation. So elastic materials undergo temporary deformation because they get back into their original position. But the materials which show plastic behavior, which cannot regain its original position, which comes under, which shows permanent deformation when subjected to stress beyond their elastic limit. So below the elastic limit, they are known as it shows the material shows plastic behavior. Beyond the elastic limit, it shows the plastic behavior. Next, coming to yield point. Here also two key aspects are there as previous. So yield point, the stress level. So there will be one yield point here like in stress strain diagram. I'll show it you later. So there below here before this yield point, this one elasticity, and after this plastic. This plastic behavior. Next, plastic deformation. So it is nothing but it is permanent and involves a change in material's internal structure. So the permanent plastic behavior is nothing but, so for any material there will be internal structure. So in plastic deformation, the internal structure, the elements, everything, molecules will be moved there and here, and the structure will be disturbed. So that in that case, the material will be in permanent deformation. So next, applications where we need to use this theory of elasticity and plasticity. These are the major things which we need to learn about them. Every material which we use or which we study here, we need to know the elastic limit and plastic limit of those. So first thing, the application is in structural analysis, means ensuring structures can withstand loads without failing. So the structures without failing, we need to construct or we need to design a structure. So we need to design whether it in a safe load. So we need not to make it like a collapsed structure, anything. So to withstand loads, we need to read about this elastic and plastic behaviors. And material design, selecting materials for specific applications based on their elastic and plastic properties. So by knowing the elastic and plastic properties of every material which we use, so in constructing a structure, so we need to know where we need to use a material, in which design, in where, which property, in which situation. So that by knowing all this, we can do the material design. And next one is manufacturing process. Understanding how materials behave during the process like forging, casting and machining. So forging, in forging also, like any material can be subjected to forging or like casting, anything. So we need to know their elastic and plastic limit and what is the behavior of the material, how it undergoes and how it deforms. Everything we need to know, because to construct any structure in all these structural engineering applications, we use all these three. So studying elasticity and plasticity behavior of any material is very important. So these theories of elasticity and plasticity provide a framework for understanding how materials respond to external forces. So by studying all those, we can understand that when we applied any load, any external load, so how does the material responds? How does the material deforms? So we can know all these, which is essential for designing safe and effective structures. So by knowing all this, we can go for a safe structure. We can design it. And next, coming to the main component, main topic in this, stress. So as we all of us know, as we studied in our BTech, that in strength of materials, what is stress, strain, Young's modulus, etc., everything. So now we are coming into the stress definition. First of all, stress at any section is internal resistance offered by material against the deformation caused by applied load. So suppose if we take a body, anything, any material, any object, when we applied load, if we by applying any load, any external load, when we are applying, for example, if you take this is a body, so we are applying it here, this is the load. So when we are applying load, automatically here inside this is a fixed, and here the internal stresses will develop. So this internal resistance offering to deformation of the body, to which it cannot deform. While applying load, it should resist the material to not get to deform. That is known as stress. So stress, how it is defined as an internal resistance offered by material against the deformation caused by applied load. So here the deformation, due to the application of load, here deformation occurs. So to reduce the deformation, some internal resistance is offered from the body. So that we call here as stress for the unit area. So it is defined as internal resistance per unit area. Stress is denoted by sigma, which is given by force load given by unit area. So this is force, this is area, and this is stress. And next, when a metal is subjected to load, it is deformed no matter how strong the material. So we cannot see every material is occurring to bending, or else it is deforming. So we cannot see every object, but it can bend. Any how much strong material also, it gets deformed, but we cannot see it. And if the distortion disappears and the metal returns to its original dimensions upon removal of the load, the strain is called elastic strain. So here the property is, when we are applying stress for elastic materials, if we talk about elastic materials, when applying load, it undergoes some deformation, and after removing the load, it regains its original position. There will get some induced deformations, and those that stress, that is elastic property of the material. So the stress induced is elastic stress, and the strain induced there is called as elastic strain. And next, if the distortion appears and the metal remains distorted, the strain is called plastic strain. Again, when the elastic body is elastic strain, plastic bodies, when coming to plastic bodies or plastic materials, after the yield point, beyond the yield point, when it does not regain its original position, then the strain developed is known as elastic strain. And next, when we go for types of stresses, each of these stresses affect an object in different ways and is caused by the internal forces acting on the object. See, when on any body, if we apply external force or any external load, the body automatically, like any beam or column, anything, any object, so they undergo some stress and strain. So how the stress and strain are undergoing and how the load is applying and how the body gets deformed, we'll see here. So first one is like compression, tension, bending, shear and torsion. These are the 5 types of stresses which the body object gets induced. So under the application of different types of loads, the body undergoes into these stresses. We'll see one by one. So first one is axial stress or normal stress. Generally, this normal stress is defined as the stress that develops when a force is applied perpendicular to the surface of an object. Let us think. This is an object. So, object plane is like this. So, when we are applying load like this, this is known as normal. The stress induced here, it is known as normal stress, because this is the object surface and it is acting perpendicular. So, this we call it as normal stress. So, by definition, we can clearly know it as the stress that develops when a force is applied perpendicular to the surface of the object. This is the object, this is a perpendicular force. So, it is known as the stress induced here. The stress induced means the internal resistance offered by the body under deformation. To undergo deformation, that here the stress induced is known as normal stress, that is shear stress, that is normal stress or axial stress. So, now it is given as formula, stress normal stress is equals to load by area, load per unit area. It can be either tensile stress or compressive stress or shear stress, any stress, but basic normal stress is under the internal resistance offered by the material under the application of load. So, next, this A is the cross-sectional area of the object. And next, when coming here, normal stress, that is axial stress. So, let us take here this body. So, some object. So, in this object, this is external force and this is external force. Two sides, the force is applied. So, then when we cut the cross section of this object, so when we make it into two parts, here this is the external load, this is the external load. And this F and this F, these both are internal forces, internal resistance offered by the material. So, to act this, so from this external forces, this internal resistance are offered. So, when we see how the stress distribution is done, so when we applying load here, like it is known as tensile load. So, by acting both sides this load, so then here the stress is distributed complete over the plane. See, this is known as all stress, these are stress, normal stress. They are distributed uniformly throughout the plane. So, this is known as the internal resistance of the plane not to undergo the deformation during the application of load. This stress is known as sigma, which is a normal stress. And next one, tensile stress. So, first stress in this tensile stress. So, we can take any body. However, tensile is nothing but stretching or pulling both sides. So, let's see the definition. Tensile stress is a measure of the internal forces that are acting on a material which is subjected to an external load or force that tries to pull it or elongate it. So, when this is the material, this is the body, any rectangular beam, you think it. So, here we are applying load, here we are applying load. This is nothing but it tries to elongate this object. This type of stress, when elongating this object, when we are applying load both sides, in opposite direction, the material tends to elongate, and the stress induced here is known as tensile stress. So, then this tensile stress is defined as amount of force per unit area of the cross-sectional area that is applied to the material to cause it to elongate or stretch. So, same thing here, sigma is equals to F by A, unit force, unit area. So, this is nothing but tensile stress. We can give it as sigma T. So, it is tensile stress which elongates or stretches the material. That is known as the stress which induced in that property is known as tensile stress. And next, coming to compressive stress. Same, which is the opposite of tensile stress. Again, here compressive stress is created by subjecting a material to force that acts perpendicular to its cross-sectional area, causing the material to shorten in the direction of the force, but it thickens perpendicular to the direction of the force. So, let us think this is a rectangular body like beam. So, applying force in this direction means it is compressing the body. Applying both in opposite directions in both sides the load, then the body again it deforms to some position. It decreases its length. Previously in tensile stress, the beam gets elongated and here the body gets compressed. So, here the thickness of this is increased. The thickness of this gets increased, and next the length will be decreased. So, material to shorten in the direction of the force but thickens perpendicular. So, in direction of the force is this. So, here it is shortening the length, and here perpendicular to the direction of the force, this is the perpendicular to the direction of the force. So, it thickens. The material gets thickens this side, it gets shortened this side. So, it may decrease in volume of the material. So, during this when this compressive check occurs, so here the volume of the material gets decreased and thickens its density because this increases. Next, coming to bending stress, another one, bending stress. So, bending stress is the stress that results from the application of bending moment to a material causing to deform. So, for any beam or anything, there will be some tensile and compressive property of for any material. So, if you take a beam, there will be it shows elastic behavior, plastic behavior. It will have tensile and compressive stresses throughout the cross section of the material. So, let's take here simply supported beam. So, the simply supported beam, one side hinged, one side roller. So, when we apply load here, we are applying load. This is a simply supported beam. We are applying load. How this body gets deformed? So, this is the neutral axis. So, upon this is undergoing to compression, and here bottom it is undergoing to tension. So, this beam is undergoing both properties, tension and compression. So, above the neutral axis it is undergoing compression and below the neutral axis it is undergoing tension. So, this stress is known as the bending stress. And next, let us take cantilever beam. So, cantilever beam is one side fixed and next other side is free, and here we are applying load at the end. So, when we apply here load, how the deformation occurs? So, the material gets deformed in this way. So, this is the neutral axis, and here opposite to the simply supported beam, exactly opposite, here on the top of the beam, top layer it acts in the tension. Here when coming to simply supported, top layer is undergoing compression, and when we are coming to cantilever, it is undergoing tension, and here bottom layer undergoes compression. So, purely opposite. So, this is known as the bending stress. And next, coming to shear stress, next one. So, shear stress is nothing but the sliding stress. So, whenever we, let's read it. The stress that results when a material is subjected to opposing forces that act parallel to each other but in opposite directions. So, I'll give you an example. So, first the formula here is torque tau is equals to F by A, and this is shear stress. Tau is represented as shear stress and F is the force applied, A is the area. So, here we can have an example. So, let us think this is the fixed support, this is the material, and we are applying load here. So, when we are applying load here, this is the fixed. So, the material cannot move from here. So, when here we are applying load F, so the material starts moving right side. So, like this. But the stresses induced during this sliding property is known as shear stress. So, the material is undergoing the sliding property, inducing sliding. So, here the material is offering some internal resistance not to slide, but due to this external load, it must get sliding. So, only some layer of the material gets sliding slides to the other side. So, this stress induced there in the body is known as the shear stress. So, next again when you see in this figure, this is the parallel forces but acting opposite directions, and next here when the stress, this is the stress distribution. So, this is the resistance of this object offered during undergoing this stress. So, PR, it is nothing but resistance. And next, coming to normal and shear stress distribution. As we have seen previous, normal stress and shear stress, let us take an example how the stress distribution occurs. So, let us take a rectangular beam. So, this is the neutral axis, or we can call this is neutral axis or centroid of the beam. Let us take a rectangular beam of width B and height H. So, here above the, generally for any beam, above the neutral axis it is a compression zone, and below the neutral axis it is as tension zone, because we will provide some bars here. So, this is tension zone, this is compression zone. So, based on the shear force and bending moment diagram, these normal stress and shear stress will be occurred. So, the distribution stress, how the stress is distributing in a beam, and how the shear stress and normal stress, how the bending moment, how the shear force are occurring. So, based on those, the shear force is One side during this side is compression, and at the center point the shear force is 0, and the maximum bending moment will be there at the center. And which is the stress, shear stress? This is normal stress and this is shear stress, because due to the starting property. And next, this shear stress will be having maximum shear at the middle of the object. Whether you take rectangular beam or circular section, anything, any beam. So the shear stress will be maximum at center. So, and it will be 0 at the ends. And when you take normal stress, it will be maximum at the edges and it will be 0 at the center. So this is the normal shear stress distribution of rectangular beam. Next, coming to the torsional stress. So it occurs when a material is subjected to a twisting or rotational force. When a material is subjected to torsion, the individual layers of the material will deform and twist relative to one another, leading to the shear stresses within the material. See, like whenever any object, any beam or anything, when we twist with both sides or twisting them. Twisting means we are acting a couple force them. So couple is acting, then the body undergoes torsional stress. When the twisting is occurs, the body undergoes, it produces internal resistance to not to undergo under that load, but automatically it gets induced some stress. That twisting stress is known as the torsional stress. And next, the formula to calculate the torsional stress is given here. Tau, that is the torsional stress, and is equals to T, that is the applied torque. Torque will get, when we apply a couple, when we apply a moment, then that is known as the torque. And next, R is the radius of the material, and the J is the polar moment of inertia. So tau is equals to T into R by J. This is the formula for calculating torsional stress. See, this is an example. So this is a rectangular beam. So when we are applying load here, we are twisting this side and this side, two opposite, we are applying torque. To both ends we are applying opposite side torque, so that twisting the beam, so that the stress occurs in the material is known as the torsional stress. And next topic is notations and components of stress. Here generally the components of stress will be the notations. In stress we have one is normal stress, and next one is tangential stress. So, by solving problems or anything, we will go through about only this normal stress and tangential stress. Normal stress is nothing but the load which is acting perpendicular to the plane, and this tangential stress is nothing but which is acting parallel to the plane. So, based on these, the components of normal stress and tangential stress are divided, and normal stress is denoted by sigma, tangential stress is denoted by tau. So, now let us see here. So, let us take this figure. Here, let us take this as x-axis, this as y-axis, this as z-axis. So now here, what are the components of stresses induced here? Let's take first normal stress. Normal stress. So normal stress is denoted by sigma in 3 axes. While we are taking here 3D, we'll get three components. Those are, in x direction we'll have sigma x. In y direction we'll have sigma y. In z direction we'll have sigma z. These are the components of the normal stress. And again, coming to now, we have defined the normal stress components, and next we need to write about tangential stress components. So tangential stress, they are denoted by tau. So how we need to write? This normal stress is completed. So now, which is parallel to the plane. So now here, the with respect to y-axis and in the component in z-axis, here the tangential stress we will get as tau yz, which is this one. And next, in x direction, y-axis with respect to x direction, we will get tau yx, which is, tau yx here. This is one. And next, again same here, we will get sigma z is a normal stress component in z-axis, and next z-axis with respect to y-axis we will get one tangential stress is tau xy, tau zy, and next in z-axis with respect to x-axis we will get as tangential stress tau zx. And next, coming to the again x-axis, here we will get tau sigma x is a normal stress, and tangential stress of x with respect to y is tau xy, and next tangential stress of x with respect to z-axis is tau xz. So these are the tangential stress and normal stress components and notations. So next, here when we take this only single plane, what are the, now this is a 3D, and when coming here this is 2D. So we are taking Y and Z plane. So we will get here only tangential stress. This tangential stress in this in Y with respect to X will get, Z will get as tau YZ. Here we will get tau ZY. This is both are positive, both will be negative. Here tau YZ. Here one, if it is one positive, then another one must be negative. So here in this right side, it is positive tau YZ, it is negative tau YZ. Here it is positive ZY, positive and negative ZY. So these are forces acting on the element about x-axis. When we are taking x-axis, the other two axes will take. So these are the components of stresses, torsional stress. So tangential stress. So next, when coming the last, as previously I said, there is a stress strain curve which represents the elastic behavior and plastic behavior of the material. So let us see here. This is stress, this is strain, represented by epsilon, and stress is represented by sigma. So here, from starting, we'll see here, for any material, when we stretch up to within the elastic limit, it shows the elastic nature. That is up to yield point. Every material has some yield point. So before this, when we remove the load, every object regains its original position if we stretch it in the elastic limit only. So below this yield point is given as elastic region, and beyond this yield point is given as plastic region. So in plastic region means when object which does not regain its original position, which shows the plastic behavior, comes under the plastic region, and then they undergoes to fracture. Fracture is nothing but the failure of any material. So this is about stress and strain relationship, and how what is the elasticity and plasticity properties of a material, and these are the types of stress. Thank you.